Welcome to lesson 3 of difference equations. This is the second of two parts on first order linear equations. In this lesson, we're going to look at loan repayments as an example, equilibrium points, and non-autonomous equations. I'm going to add a constant to the geometric difference equation that we had from the last lesson. That's the b that I've added here. So this is still first order. It's still linear, and it's still autonomous, but it's not homogeneous now because we've added a non-zero b. We can find the solution to this using our general formula from lesson 1, which I've copied down here at the bottom. You notice the a of I is just a all the time, so you get a to the n here. Then when you multiply these together, you're just getting a squared, a to the minus 1 times, and b is the same in every case also. So you just get this here. Another way of doing this is just start from x0 as the given, and then compute x1 from this formula. Then plug that in to get x2, and you'll see that this pattern is developing here. Now there's a closed form for this sum, which I'll show you on the next slide, and then we'll do an example. Concerning this sum and the formula from the previous slide, this is what I'm pointing to here. If you multiply this by 1 minus a, then you get a lot of cancellation, and it equals 1 minus a to the n. And then you can just divide 1 minus a on both sides, and then this sum is equal to this closed form here. So this is easier to work with. You may have seen this before. It's just the sum of a finite geometric series. Okay, so this is our equation, and now we'll make use of this in an example. Our example is a loan repayment. First we'll set it up, and then we'll give you a general solution. So the amount borrowed is Q, and it's to be repaid over n equal periods. The interest rate per period is I. The payment each period is A. Each period, the balance grows by the interest owed, then drops by the payment. So if you make a loan for $100,000, for example, and the periods are monthly, then at the end of the month you would owe interest on that 100,000, but at the same time you would be paying this amount A, which would be part interest and part paying off the principal. That's what I'm saying here. So the whole question is, what must A be so the balance reaches zero exactly at period n? So that's what you want to solve for, is A. So in terms of our equation, x0 is Q, x sub n is 0, so we want to finish by not owing. So this is kind of a downward spiraling series, which we haven't seen yet, but it's quite possible to go down. Of course, we stop after this. You don't keep paying the A after you've already paid off the loan. So this is a finite series. And then A is 1 plus I. We get that from here. Let's just go through this slowly. So this was the amount that you still owe, and then you have to pay the interest over that one period. That's I, right? Interest rate per period. And then you subtract your payment A. So you can just factor the x sub n out, and you get this here. And this is the form that we've just saw in the previous slide. Was the A now is 1 plus I, and B is minus A. So we want to solve for A. We'll do that on the next slide. I brought over our equation from the previous slide. Remember, A is 1 plus I, and B is minus A, and then this was the general form of the equation we started with, where we added a b to the geometric series. And so we just plug things into here. A is 1 plus I, so you get 1 plus I to the n. X sub 0 is q. Then here I did a few steps, and I didn't show them all, but I'll explain them here. So b is minus a, but then 1 minus a is 1 minus 1 minus 1 minus I, so it's just minus I. So the minuses cancel out, and you get a divided by I. And then this part here, 1 minus a to the n, is 1 minus 1 plus I to the n. So remembering, we're looking for a, but we're also told that when n is equal to capital N, this is equal to 0. And so I just subtracted this from the other side. You notice I have instead of 1 minus this, I have this minus 1 because I subtracted it. And then we divide by this into this side. And we get this here. And if you notice, the bottom has a minus n here. That's because I divided the top and the bottom by 1 plus I to the n. So it cancels out at the top. And then on the denominator, you just get 1 minus this here. So A depends only on three things: the amount borrowed, Q, the rate per period, I, and the number of periods, N. So there you have it. It's a useful formula for computing the amount, the payments on a loan, given the three quantities we just mentioned. I have a simple example using our formula from the previous slide, which I copied down here. So we have $25,000 borrowed for a 30-year mortgage at 3% yearly rate, nominal rate for the year, repaid in monthly installments over 30 years, and we want to find A. So N equals 30 times 12. That's the number of periods. The rate is 0.03, the nominal yearly rate divided by 12. And that gives us our I, 0.0025. Q is 250,000. And we just plug those in, use a calculator, and we get 1,054 and 1 cent. So, and then this is just a graph showing a rough, very rough graph, just showing how this is going down to 0, the amount of money that's still owed. And of course, you're paid off at 30 years. Now, a change of subject and a concept that will matter a great deal in lesson 6. In general, an equilibrium point for a difference equation is a value x star with this property, which I'm showing up here. If x sub 0 equals x star, then x sub n equals x star for every n. So it's basically this equation here. I've just plugged in x star here for x n plus 1 and x sub n. And then you solve that and you get the equilibrium point for our linear equation with the forcing term b. We can double check that. We can put it into our formula that we solve for. X sub n, we just put in this term here for x sub 0, or well, actually x sub n minus 1, since we're looking for x sub n. And you get a common denominator. You notice the an and the an, these cancel, and you just get b in the numerator, and you get b over 1 minus a. So that checks out. When a is equal to 1, then you can't have x star equal x star plus b unless b is equal to 0. So that's just a special case. I have two different examples on this slide. It's only one of them that relates to the title. The first example shows you can have more than one equilibria. So So you notice if you put in 0 for x, you get 0 again and 0 again. And if you put in 2/3 for x, you get 1/3 times 2 is 2/3, and you put it in again, you get 2/3. So this is a bit of a contrived example, but it illustrates the point that you could have more than one equilibria. And then this is the second example is eventual equilibrium. Again, it's a bit contrived. X sub n equals 2 to the n minus k, as long as n is less than or equal to k. So you start at 1 over 2 to the k, and then you multiply by 2, and you get 1 over 2 to the k minus 1, all the way down until 1. Right, that's when n equals k, and you get 2 to the 0, that's 1. And then we define x sub n equals 0 for n greater than k, and you flatten out the 0 all the time, just by definition. And so that's an eventual equilibrium. So let's change the topic slightly again. Now I want to talk about when the coefficients vary. So we had constant coefficients, but you see in these equations, difference equations down here, you have now n squared times xn. Your b now is varies based on n. And then here you have both, right? You have a variable coefficient for xn and your bn. So this is kind of the most complex. These two are non-homogeneous because your b is not equal to 0. This is homogeneous, but it's non-autonomous. In fact, all three of these are non-autonomous. The homogeneous case, this one here, is the one that stays tractable with every bn, right? There's no bn here, bn equals 0. The general formula reduces to a running product alone. Just continuing with what I said on the previous slide. So when you have this form of b of n equaling 0, and I said it's just the product of the coefficients. So that follows from here. I copied the general formula from lesson 1 down here at the bottom, and if the b's are all 0, then this all drops out, and you just have this here. Then I have two examples. Here you have your a of n is r to the n. And when you multiply these out, you're just getting the exponents are added 1 plus 2 all the way up to n minus 1. And that sums to n times n minus 1 over 2. So you get that here as the product of the a sub i's. Or in this case, we're going up to n plus 1, so you have an n in here. And then in here you have 1 over n plus 1. That's our an. And so that the product is just 1 times 1/2 times 1/3. So it's just x0 over n factorial. So they're not always that easy, but in this case here, the product results in something that's in a closed form that we can work with. I have a story about the famous mathematician Carl Friedrich Gauss. When he was a young student in grade school, the teacher asked the students to add all the numbers from 1 to 100 just to keep them busy for a while. And Gauss had the clever approach of adding 1 to 100, getting 101, and then 2 to 99 and getting 101, and so forth. And basically he saw that if you line up from 1 to 100, and then underneath of it you line up from 100 downward to 1, and you add each of the terms together, you're going to get 101 100 times, and you divide by 2, and you get 5,050. So he was surprised his teacher, and I guess the class too, that he got the answer so quickly. And basically this is the formula that we use for the sum of the first n numbers on the last slide, n times n plus 1 divided by 2. I heard another story which I'll relate. I'm not sure if it's true, John von Neumann, also a famous mathematician from the 20th century, the story is he was given a similar problem to his class, and he came up with the answer really quickly. And he was asked, "Well, how did you do it?" And he said, "I did it in my head." So that's maybe typical of von Neumann. From what I read about him, I think he learned like 6 languages before the time he was even 10 years old. So you have some amazing stories from these child prodigies. Here's an example of where both the coefficient and b of n are not constant, they're functions. So here we have a of n is n plus 1, and b of n is 2 to the n plus 1 factorial. I copied our general formula down here, and what we want to do is plug a n and bn into this, and then get it into closed form, which I have here at the end. So that's the point of this. Sometimes you can, even if you don't have constant coefficients in Bn being constant, you can occasionally, not always, but you can sometimes get it into a nice form like this here. So this is easier. This product, it's just 1 times 2 times 3 all the way up to n. So this is n factorial times x sub 0. Then this side's a little bit harder. First we'll do the product, which I've shown here. We just put in ai, which is I plus 1. And so when you multiply this out, it's j plus 2, j plus 3, up to n, which we can write as n factorial over j plus 1 factorial. And we do that because we get some cancellation when we plug this back into the summation here. So we plug this into here. This is b of j. So 2 to the j plus 1 factorial. You notice these cancel out. And I should note that I went up to n minus 1 here rather than n minus 2 just to suck in this term. Because if you plug in n minus 1 here, you get n factorial divided into n factorial, so that's 1. And then you get 2 to the n minus 1 n factorial, which is b of n minus 1. So that I brought everything into one summation. We get the cancellation, as I mentioned. We can bring out the n factorial, and then the sum from 0 to n minus 1 of 2 to the j is 2 to the n minus 1. That's just a finite geometric sum. So we have this here, and then I just factored out the n factorial because it appears in this term and this term. And then you get our final solution here. The lazy caterer sequence is a problem whose solution involves a recurrence relationship, a difference equation. So we first need to set this up. The question is fairly simple. What is the largest number of pieces a circle can be cut with n straight lines? And I have a running illustration here on the right. Let's just wait for it. Here we go. So the first one is 2 and then 4. The third one cuts it into 7 pieces. It's a little bit hard to see here because the regions are very tight to the circle. I'll show you more detail on the next slide, that situation. So to obtain the maximum number of pieces, the nth cut line should cross all the other previous cut lines inside the circle, but not cross any intersection of previous cut lines. Thus, the nth line itself is cut in n minus 1 places and into n line segments. Each segment divides one piece of the existing divided up circle into 2 parts, adding exactly n to the number of pieces. The new line cannot have any more segments since it only crosses each previous line once. So in going from one step to the next, you're adding n more pieces to the fragmented circle. So that's key. We'll need that when we set up the recurrence relationship. Now, if you look at the Wikipedia article, and I give you a reference to it, you can just search under lazy caterer, and it'll be, I think, probably be the first item that comes up. If you go there, it'll kind of show you the dissection of the circle in a sort of an ad hoc way, and it's not convincing that you can actually do what I wrote in this paragraph here. So I searched around and I found this is more of a method of doing the dissections. You start with a little circle inside the circle in question, and then you just start drawing uh, tangent lines, slightly rotated uh, along the smaller circle, and that gives you a method for dividing up the larger circle. So I have it explained here. Such an arrangement always exists and is easy to describe. Well, I don't know, maybe I'm exaggerating here, but place a small coin at the center of the pie, that's the orange one here, and make every cut tangent to it, with all points of tangency lying on the same quarter of the coin's rim. So you only want to go a quarter of the way around. If you allow it to go all the way around, then you have the possibility of, or even beyond a quarter, you have the possibility of having parallel tangent lines, and then that messes up what we're trying to do here. Two tangent lines to a circle can be parallel only when they touch at opposite points. So no two of these cuts are parallel, and every pair crosses. That's because we're only going a quarter of the way around. Because the tangency points are confined to a quarter circle, those crossings occur close to the coin, and I'll show you that on the next slide, and therefore well inside the pie if the coin is sufficiently small. Finally, no three cuts can pass through the same point, since from any point outside a circle there are exactly two tangent lines. So in other words, a point out here and this little circle there can only be 2 points through that point and tangent to the circle. Okay, so let's look closer inside of the circle around this coin in the middle. I'll show you that on the next slide. So here I'm zooming in. This is the little circle, the coin in the center, and we're only going a quarter of the way around. So it's basically you can see this is a square where I'm pointing here, and um, the distance between the center of this little circle and out here is the square root of 2 times the coin's radius. So that's what this dashed line is here. So you want to have a coin small enough so this dashed line doesn't go outside of the bigger circle. So if we zoom in, you can see this, say that's the first one, then the second one is this one, then the third one. And you notice they're cutting out little regions very tight to the circle. So the first time you cut it in half, you get 2 regions. They're not, of course, of equal size, but you get 2 regions, and then you do it again and you get 4. But then the third one gives you 7, and you get to see regular. Well, you get this pattern as you proceed, and we'll compute exactly what it is with the recurrence relationship. Okay, so I'm doing this mostly to convince you that this is possible, and that you add n more regions on each, going from step n minus 1 to n. And once you accept that as being possible, then the recurrence relationship follows pretty easily, and I'll show you that on the next slide. So as I described earlier, the number of regions added in going from step n to n plus 1 is n plus 1. So this is our recurrence relationship. It's pretty easy to solve. I put our general equation down here, but a is just 1. So this part of it is 1 times x0. And then here we just have 1 times bj, but if you put in, you start at 0, so it would be 1 all the way up to n minus 2, which would give us n minus 1, and then b of n minus 1 is n, so you get this here. And from the example I gave you, or the story I gave you from Gauss, we know that this sum is n times n plus 1 over 2. We just plug that in here, add 1 to it, and we get our final result. So a quick review of this lesson. We added a constant b, and that gives a two-term closed form val when a does not equal 1. So we went through that. Then we did a loan repayment example, and we took it, and once we derived the formula, we took a particular mortgage, and we computed the monthly payments in order to have the mortgage be paid off in 30 years. Then we talked a little bit about an equilibrium point. Then I gave you an example of a more complex recurrence where the coefficient as well as the forcing term were functions and not constants. And then we just went through a fairly well, easy to solve problem once you have the recurrence relationship, but maybe a bit hard to actually reason to what that recurrence relationship is concerning dividing up the circle. So coming in lesson 4, we'll talk about higher order difference equations when a term depends on two or more predecessors. This is an example we'll start lesson 4 with. You notice you need to know, in order to compute x sub n plus 2, you need to know two previous values. We'll talk about the characteristic equation and why guessing a power works. We'll talk about the Fibonacci sequence, the golden ratio, and Benet's formula. We'll talk about repeated roots, that's related to this equation here, and the exact factor they need. And then it's also possible, this characteristic equation can have complex roots, so we'll deal with that case too. So don't forget, if you like this lesson, please give it a thumbs up and consider subscribing to my channel.